All right, hopefully you have your notebooks out, ready to take some notes on section 5.5 of AP Calculus. We're going to talk about applications of derivatives using linearization and Newton's method. And what you can do, watch this video at home, you can take a look at these quick review problems if you haven't already and work on them. And then what I'm about to do is show you a slide with answers. So I'd pause on this and then I would answer them, and then here are the answers. So pause if you don't want to see them. Pause. So here's the answers. You don't need to do that in class, but there they are. You can pause to see those. So what you'll do here today is we're going to talk about linear approximation, differentials, estimating change with differentials, absolute, relative, and percent change. We probably won't talk about that a lot, or sensitivity to change, but we will also talk about Newton's method. Basically, what we're talking about today is different ways to approximate different values of a function using calculus, using derivatives and applying different methods, equations of tangent lines especially. So to get started here, there's a little bit you need to know. We've talked about this before. The tangent line to a curve provides a useful representation for the curve itself if we stay close enough to the point of tangency. Okay, so what we're going to be doing is we are going to be using the equation of a tangent line to actually find approximate values of our function, so long as we don't stray very far away from that point of tangency that the tangent line comes from. And then differentiable curves are always locally linear. That's something you want to keep in mind. Remember, if you zoom in close enough to see, if you zoom in close enough, you'll be able to see this because the actual graph will look linear. We've talked about that in the past. So to get started, we're going to talk about linearization. Now don't get confused by all of this. What this is basically doing is it's saying if we pick some differentiable function f and we pick a value a to write the equation of a tangent line, we're going to call that L of x. So that's nothing new to us. This L of x is simply what we're calling the equation of our tangent line. What we've done in the past is we've wrote this f of a, that's like our y value, our y coordinate point. Our y value when x equals a is f of a. And we usually just wrote that over on this side. This is just the equation of our tangent line. So that's the equation of our tangent line. And it defines the linearization of f at a. So if you find that phrasing somewhere, it's talking about writing L of x. And L of x from now on is our equation of our tangent line. And that's going to give us an approximation for f of x. Again, if we don't stray too far away from the a value where L of x came from, L of x is going to be an approximation for f of x. It's called the standard linear approximation of f at a. And then also to note, x equals a is what we call the center of the approximation. So again, what we're going to be looking at is we're looking at values close to a, and we're actually going to plug those values into our equation of our tangent line to get approximations for our function f. So if we are asked to find the linearization of f of x equals cosine x at x equals pi over 2, and use it to approximate cosine of 1.75 without a calculator, what we're going to do is we're going to find the equation of our tangent line. So to do that, we are going to need to know, if we're looking at x equals pi over 2, we're going to need to know the y value we get when we plug in pi over 2. We're going to need to know the slope when x equals pi over 2. Well, how do we get the slope? We find the derivative. So those are all things that we need to know which, real quickly, f of x is given to us as cosine x. And that's as cosine x. F of pi over 2, so that's cosine of pi over 2. And you all know that's 0. And then the derivative of cosine x is negative sine x. Well, we need to know the slope at pi over 2, so the derivative at pi over 2, sorry, that's a little sloppy. I'm writing with this old computer pen. Get over it. That's going to be negative 1, of course. So, again, put all that together to write the equation of your tangent line like you have in the past. This is the new way of organizing it. But so we know the y value of the point we are using is 0. The derivative at pi over 2 was negative 1. And then we have x minus pi over 2, which equals negative x plus pi over 2. So we've got that going. So that is a linearization of f of x at pi over 2. So now if we want to approximate the cosine of 1.75, we are going to use the linearization to approximate that. So what I'm going to do is I'm going to plug in 1.75 into my equation of my tangent line. So this approximation is going to be negative 1.75 plus pi over 2. And that would be your answer. So that value is approximately negative 0.1792036.732. So that's what we get for a value. That's our approximation when x is 1.75. Now, what you'll be asked in your book is also to find to determine the accuracy of the approximation. So what you're going to do then is you're going to find the absolute value of the difference between that number you just found and the actual answer you get when you plug 1.75 into the function that you started with right here. So if you do that, just find the absolute value of the difference, you're going to get, you actually get a positive answer, of course, if it's absolute value. 9.576 times 10 to the negative fourth. Well, we don't have to be that specific. That's going to be our approximation error. What we'll say is that we would report an error of less than 10 to the negative third, and that's how you'd answer it. So that's pretty accurate. Next, I want to talk about differentials a little bit here. Remember, dy dx represents the derivative of y with respect to x. Notation, it looks like a quotient, but really it's a limit of quotients in which both the numerator and the denominator go to 0 without actually equaling 0. So it's tricky to define dy and dx as separate entities, since we only need to define dy and dx as formal variables. We define them in terms of each other. So their quotient must be the derivative. So basically what we're going to do is we're going to treat dy and dx like variables, where dy is dependent on dx and x. So what that's going to look like is here. This is our definition then. If we let y equal f of x be a differentiable function, the differential dx is an independent variable, and the differential dy is defined as f prime of x times dx, where then the differential y is always dependent on dx and x. And then you can kind of see how that manipulation occurs. If we take dy equals f prime of x dx and we divide both sides by dx, we get our derivative that we've been working with, f prime of x. We also can write write dy as df, where we call that the differential of f, and that's going to equal the derivative of x, or f prime of x, times dx. An example of that is if I wanted to look at the differential of the function f, that would be the same as taking the differential of 3x squared minus 6. So obviously the function is 3x squared minus 6. The answer to that would be 6x dx, because you take the derivative of this just like normal. 2 times 3 is 6x. The derivative of negative 6 is 0. And you just tack on that dx at the end. And then this is in your book also. I just wanted to show you different forms of, or different ways to write these same things we've been working with. I know a lot of times what can be real confusing is all these different letters that are attached to these d's, and when do you write what and where, and how come there's so many options, and so I like to just give you some options. If you have questions about that, ask. It really just takes some reading of this section and kind of studying the different answers that are given in the different examples, and basically realizing besides f, the main time that you have different variables used is when there's a different variable in your function. So put some work into reading those and be ready to ask some questions. So here's an example of finding the differential of dy. So if I'm finding the differential dy and evaluate dy for the given value of x and dx, well, finding the differential is easy. You just take the derivative of this like you normally have in the past, and you tack on the dx at the end. So then that's that right there. Now, if they give you an x value and a dx value, you just plug those in for x and dx, and you have what dy is at x equals 1, and that change in x is just 0.01. Then you find that value is, your change in y is going to be 0.07. Okay, so with that said, I mean, that's all you have to do when you're asked that type of question. We use differentials to estimate change. Suppose we know a value of f, the value of a differentiable function, f of x, at some point a. And we want to predict, looking at some point a to plug in for x, we want to predict how much the value will change if we move nearby point to point a plus dx. So we're just adding a little bit to a. We're just going a little bit away from where a is. We want to know how much the value of our function changes just by changing x a little bit. Well, if dx is small and our function if dx is small, f and its linearization L at a, at that point a, will change by nearly the same amount. So what that's saying is we can use that linearization we talked about at the beginning to find that change. So the values of L are simple to calculate. That's why we do this. The values of L are simple to calculate. It's just a linear function, and offers us a practical way to estimate changes in f without having to go through a lot of work. So that estimate of change is found by if f of x is differentiable at x equals a, the approximate change in the value of f when x changes from a to a plus that small amount dx is equal to, when we take the derivative and multiply it by that dx value, that difference in a and a plus dx. So that's all you have to do is take the derivative and multiply by that difference. We'll do an example here, but first I wanted to show you a little diagram of what's happening there. So the a value we're looking at is right here. Right here this is the a value, and what we're doing is we're just going to add d of x amount to it. When we add this d of x amount to it, we want to know how much that y value ends up changing. And what we do is we use this linearization. So here's the equation of our tangent line, and we're going to take the derivative and take a look at that change here, but we're going to do it by using the change in L. So down here I've written up how that change that we're looking for up here corresponds to the change in L. You know, this change in L, this is our equation of our tangent line. This is how we got it, and that simplifies down to just taking the derivative, multiplying by that change in the A value. So with that said, let's just do an example here before the video gets too long. I know you don't want to listen forever, although it's so interesting. Anyway, so what we're doing here is we're using these differentials to find how much changing one aspect of our situation will change the outcome. So an example of that, maybe we're looking at a cylinder, and maybe our variable that we're changing is the radius of the cylinder. Well, we would be able to show how a small change in the radius of a cylinder affects the volume of that cylinder, or affects the surface area of that cylinder, and so on and so forth. In this example that I'm about to go through with you, we have a radius of a circle increases from 5 to 5.1 meters. We're going to use the differential of A to estimate the increase in the circle's area. So when the radius increases from 5 to 5.1, we'll use that differential to estimate the increase in the circle's area. Now you know the area of a circle is pi r squared. The estimated increase is going to be when we differentiate this, or find its differential. So dA is going to equal, if we find the derivative of this, it's going to be 2 pi r dr. Normally we'd say dx, but the variable is r, so we'd say dr. Well, now we know what r is. It's 5, so I'll plug that in. And then the difference here is going to be the dr. So dr is 0.1. Plug those in, we get our answer. What that means is our estimated increase is going to be, when we increase that radius from 5 to 5.1 meters, our overall area increases by pi meters squared. So that's just good stuff. And that's good application that we can use there. Now all this will be on the website. I'll tweet it out, and you'll be able to watch and pause and do more things. But the last thing I'm going to talk about is Newton's method. With Newton's method, basically what we're doing is, it's a little bit outdated because we have our graphing calculators and we have other techniques, but basically what happens with Newton's method, the idea is that we're trying to find the zeros of our function. And what we do is we use the equation of our tangent line, or the linearization of our graph, at some x value, some x value that we pick that's close to where we think a zero is. So that's where you have to approximate and kind of guess. So you pick that, you find the linearization, and what Newton's method does is we have this formula for finding the zero, and it's this, and it takes a few tries, but what we do is we first guess. So our first x sub n, so our x sub 1, that's going to be our guess. Now you want to be close to accurate. You can't be really far off for this to work, but you want to be close. And so what you do is you plug x sub 1 in to this equation, where we have x sub 1 in that case, or x sub n, minus our function, where we plug x sub 1 in, divided by the derivative of our function. Now what that's going to do is that's going to give us where our tangent line at x sub 1 crosses the x-axis. So that's going to, in a sense, give us our x sub 1 plus 1, or x sub 2, if you will. So that's going to give us this value. Well, then what we're going to do is we're going to repeat that. We're going to take this value that we found when we plugged in x sub 1, we're going to plug that now in. So this will be x sub 2 is our result. We're going to plug that back in, find this equation, and then we'll get our x sub 3. And we're going to get closer and closer to the actual 0. And we'll be able to see that we're closer and closer when the decimals stop changing of the zeros we get, or once we get so far out they're not changing anymore. You'll see an example here. So this process that I just described is Newton's method. You first guess the first approximation to a solution of the equation, and then you graph y equals f of x. Or you can graph y equals f of x to help you find that guess, or maybe you just have a good guess. And then you use the first approximation to get the second to get the third, and use this formula to do that. So an example of that here, we'll use Newton's method to solve this equation. So what you do, you need to find the derivative first. So you know what the derivative is. That's not hard for you. You got 3 times x squared plus 3. And the derivative of constant 0. There's your derivative. So now your function is going to, or the equation that we use is right here. This is where we have to plug in an approximation. I've got a graph over here. Let's say that the 0 is approximately negative 0.3. So if we use negative 0.3 for our approximation, that's going to be the x sub n that we start with. So now I'm just going to rewrite this where I plug in f of x and f prime of x. And that's right here. So now I'm going to plug in, what you should do is you should plug in negative 0.3 here, 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 and here, and see what you get for an answer. So our x sub 1 is going to be negative 0.3. When you plug all that in, you should get this answer. Now you go back and you plug this back in again to those x sub n spots, and you get this answer. Then you go back in, you plug this answer back in, and you get this one. And now if you do that again, I believe we're at the point now where you plug in this, you're going to get the same answer back out. You plug in that, you know it's going to be the same. So for all the x sub n for all n greater than or equal to 5 appear to be equal to x sub 4 on your calculator. So the solution is what we just wrote right there. And so that's where we would end it. That's our approximation, and you can compare that to if you actually find the 0 on the graph, and it will be the same as this. So with that said, the last thing I need to do is warn you that this Newton's method, it may fail. Okay, it's a numerical technique for approximating zeros. Under favorable circumstances, the zeros of linearization converge rapidly to an accurate approximation, but it may fail. Newton's method, and this is straight out of your textbook here, Newton's method does not work if f prime of x equals 0. So if the point you pick is a 0 of the derivative, then it's not going to work. You got to choose a new starting point, and you can choose one that's just close to that. It also does not always converge. So for instance, if you look at this graph over here, successive approximations r minus h and r plus h can go back and forth between the two values, and no amount of times that you plug that value in will get you closer to the 0. It'll just keep going back and forth. So that, there are cases where it doesn't work. Also, it doesn't converge. If it does converge, it will converge on a 0. However, you got to be close. If you're not close enough to the 0 that you're trying to converge onto, you may converge onto a 0 you didn't try to find. And you can see that here. This one, here's the first tangent line we used. Well, that was too far away from this one we were trying to get, which meant it went to the wrong 0. So that's the lesson. Again, this will be posted. You can watch it as often as you need. Hope you enjoyed.